3 learning objectives. I feel like this is something that you have a basic understanding from being a person who exists in this world and generates waste. You probably know what waste is, but in a good textbook environmental science kind of way, I want to think about waste in a really in a specific context. But it's material outputs. So we're not talking about waste of human capital or waste that could be associated with things you know in other classes. We're talking about actual physical matter that is an output from a system, and usually that system is an economic system. We're making goods that we want to sell, and so there's waste associated with that, and then there's waste associated on the back end. And the one that we're really going to focus on today, but there are other kinds of material waste, byproducts, liquid byproducts, air byproducts created, those are waste as well, but we're really going to focus on solid waste here and municipal waste. Municipal solid waste is all of the waste that comes from small businesses and industries, municipalities, institutions like our school. We all generate waste, so we're going to be focused on that. But here's where I want to spend on these 2 figures as kind of the main part. If you turn your attention to the figure that's at the top right, this is a painfully oversimplified version of a process. A process has inputs. I want to make something. I need some key ingredients. Those are all considered inputs. You're going to put that into a production process. You're going to make whatever you're going to do. Process also includes how it's going to be used. So as an example, if I'm wearing shoes, we have to have inputs for those shoes. I need material. I need some polymers. In this case, I needed leather. I need some rubber for the soling. All those are inputs. And the process part includes making those and me wearing the shoes for the lifetime and the use of the shoes or whatever product. And then we have outputs. So part of this is we have waste that comes out of this process during the making. So there's part of the materials that we can't use to make the actual products. All of that is waste. Likewise, there's waste associated when I'm done with the shoes and I no longer want them. They have to go somewhere. So there's waste coming out of this process in a couple different key ways. So when we're thinking about waste, I want to view it in this specific way. We're thinking about it as where does it reside within a system, and then we want to think about where it goes. Solid waste stream can contain all kinds of materials that end up from different sources, and they may end up in different places. So its final destination, or what we would call its fate, is going to be dictated a lot of times on what it is. And we're going to call that whole thing the waste stream. We have a process, and we're moving things through like the way a river flows. We have a stream of solid waste material. And I just want to point out here that the waste stream includes everything that's recycled or it's incinerated, which is one of the places that one of its final destinations it can end, or a landfill, or it's disposed of in any way. So this is where the waste goes, that movement of the waste and the tracking the waste as it moves through a process. That's what we're going to call the waste stream. According to the narrative, and like I just said, we're living in a unique time where we're starting to see and understand the impacts, the the environmental impacts of our population, our affluence, and our technology. And one of the ways that this is the most evident is in waste. This figure's from your textbook. I think it's pretty good. It's a time series starting in 1960 and going to about the recent publishing of the book in 2010. You can imagine what the trajectory of the line looks like beyond this. Over here, this is a dual axis, so what we're looking at on this side is the total municipal waste generation in metric tons, and that is a blue line. So this is a trend. And then another trend that we care about is the per capita. So how much waste is each individual creating? And we see. When you look at this, what 2 trends are evident? First is what trend is evident around the total waste produced? Going up, going down, or steady? It's increasing, right? It's obvious, the blue line. What do you notice about the per capita? So how much waste is being generated per person? Is it going up? Is it steadying out, or is it going down? What do you think the trend is going to be from 2010 to maybe the year 2030? It's the orange line. It might be decline, it might be steady out. So on one hand, I find this a little discouraging thinking about what's happening with waste generation and waste disposal. It's going way up, but I also look at this line and say every individual is doing more than they've done in the past to help reduce the amount that they're producing. So what accounts for the difference? This is population, right? If everybody's using less but the line is still going up, that means that we must have more people that are generating waste. Makes sense, right? All right, here is where the calculation comes. I want to do a little bit of proportional math practice, a couple 4 questions. We'll take 3 minutes to do this. So here's this figure, again from the textbook, really great, but I want to think about waste in a couple categories, and I want to put some numbers behind it so we can actually think it out here. So we'll take 3 minutes to do this. Okay, great. Hey, I want to look at these numbers. I put this calculation exercise together for a specific reason to also show us something. Part 1 is it just shows you that proportional math is key. We've come back to it time and time again, this sort of simple algebra and this dimensional analysis. But number 1, the total amount of compostable material, what did we come up with it for an answer there? Who can give it? Yeah. 77 million tons, right? U.S. tons or metric tons. So we're talking about a ton. Imagine it's like the same weight as a pickup truck, and we have 77 millions of that ton produced in the United States. Okay, what else? Number 2, the amount of paper recovered. Let me come back to that one actually. Number 3, how much is per household? Yeah. Per household? Is that, I think there might be a digit off, maybe. 2 tons, I think, is about, I think you might have had a decimal off. 1.98 tons per household, right? Okay, great. About 2 tons that's made by every individual house. Take a second for that to sink in for a moment. One of the problems about waste as an issue that our society faces is we generate waste, you put it in a waste paper basket, and it goes away from you. And you no longer see it. In your mind, that problem no longer exists. If you had to deal with 2 tons of trash sitting in your enormous problem. But we've created a huge infrastructure and a methodology for removing waste from individual houses, institutions, small businesses, etc., that municipal solid waste, and taking it away so you don't have to deal with it. But that doesn't mean that it doesn't exist. So seeing if it was piling up and knowing that it's about 2 tons should mean something to you. The amount of plastic material recycled and number 2 and number 4 in my mind kind of go together. What about number 2? What did we come up with for number 2? How much paper? Yeah. 41.87 million. So 48 million tons. So we have this huge amount of paper. What about the amount of plastic material compared to how much is generated? Number 4. About 8%, is that right? Is that what other people came? Agree or disagree for number 4? 8%? 8%. So, on the very first slide when I introduced this, I said the fate of waste is largely dependent on what it's composed of. So we have this amount of paper. We see about 8% of plastic. So we're dealing with waste in different ways and dealing with that matter based on what its composition is. That will be important. Number 5, thinking of a couple ways that waste or which types of waste are from non-renewable sources. So anything that's made from living material that can be replenished, all those would be renewable, but things like metal cannot be replaced. Things like plastics that are made of petroleum, those cannot be replaced. They're non-renewable resources. All right, great. So now we have our minds a little bit around this total quantity issue, and we're going to think about, well, how is it dealt with? I just said we have this infrastructure and this process put in place to move waste from one place to another. Let's look at it. This process is kind of important, and I want you to focus on the picture on the right. First, just want to walk through the basic stages. This is a view from about 10,000 feet, but each one of these stages does matter, and we'll come back to key terminology to it here in a second. But basically what we have is waste is generated by some place. It's transported. So we have waste and energy, and we have all of these inputs that go into the stream associated with just moving it from point A to point B. Of this process, that's a big energy push for transportation for something that maybe doesn't even need to exist. That's stage 1. Stage number 2 is it's not in its most compact form. So if we want to minimize the amount of space that all this waste takes, it's in our interest to do that using machinery called a compactor. So waste is compacted by specialized machinery. They pour it all in from trash trucks, etc., and it jams it into super small cubes or small shapes, and it can be baled, and it takes up less space. And that's in our interest to do that. The next thing is we have some pollution or some, it says leachate. I'm going to loop back to the definition, but I just want you to understand that some decomposition and breakdown of the material occurs over time, and we have to have a way to collect that. Because the process, natural biogeochemical cycling is taking place and movement of material is taking place as it changes states of matter over time. So we have to collect that up. The next thing is the landfill is capped and covered with soil. So we're going to try to isolate the damage that this trash or this solid waste can do in the environment. So we cover it up, sequester deep underground, and that minimizes impact. This is a stage of a more mature. So after we filled up a certain space, you'll do this stages 1 through 3 for a long time. and then you'll convert it in stage 4 to something like this. And then what continues to occur is more breakdown, and when we have methane being produced, and we have to have a way for that to come out, otherwise it creates an underground fire, or it can create an explosion. It's very explosive. It's a combustible. So let me loop back here and just look at the definitions that I want you to know and give them to you now that you can put them in context. Leachate, that contains elevated levels of pollutants, so it's something that has the ability to cause harm. Pollutants, we're that space now, but you can put in your mind anytime we're talking about something that causes harm in the pollutant, a material that causes harm. So here we have liquid pollutants that are created as part of this process, and they pass through and they can contaminate the soil. So even though this is underground, don't lose sight of the fact that it still is causing harm in the environment. It has the ability to cause harm, but we've kind of concentrated it in certain areas. So hopefully it's only causing harm in areas in close proximity to the landfill. But leachate, that is one key thing that we need to know. A sanitary landfill is what we're calling the thing. So we're calling this sanitary not because we've cleaned it and disinfected it. The sanitary piece just means we've engineered a solution to try to isolate the harm that this could cause by putting it in a certain area, and that area away from human populations, and hopefully minimize ecological impact. So we're not cleaning it, we're just sequestering it. The next thing is a tipping fee. This comes from the text, a key term of it's a fee charged for disposing of material in the landfill. So if you take extra material that you create beyond the normal, you have to pay a certain amount to deal with that, and that helps pay for all of this, but it also enters the economic system where it's in, if you have to pay money to dispose of waste, then you're less likely to create it. So it has an economic component. And then the last one here is sitting, the designation of a landfill location, typically through the regulatory process involving studies. So what we're saying with this is have a process in place that helps us say this is where a landfill should be. That way we don't have many landfills wherever. You don't just have a landfill in your backyard that's just for you. We have a sitting is this process where we've undergone a certain process to decide, hey, this is the best place to put it. So we have 4 key terms, and all these refer to just our normal, just getting our minds around what does a regular look like. Everybody had time to pen these quick definitions down? What?
It's like 15 more seconds.
Got you. Got it. Totally got it. I'll just mention here, the better that this sitting process is done, the less the impact on the environment is. And there's a lot of science that happens in this space. People who are doing analyses of water, soil, ecology to make sure that these are in the best possible location. So there's a lot of science that happens here. It's a huge amount of material that's been artificially created, and it creates leachate and all kinds of. There is going to be harm. There is not a situation at this moment in time where we have a landfill that has zero impact on the environment. There are environmental consequences associated with the fact that we're creating all this waste and we're disposing of it in a concentrated location. Here are what we're talking about. No matter how well we do it, even in its best state, there's always a possibility that leachate can get out because of environmental disruption. That could be something like a small disrupt the way the sanitary. We don't have processes and structures in place that can protect landfills from everything. There's a potential that leachate can get out into the environment. That's key. When it gets out, the way that we're most concerned about is this leachate making its way into water. Number 2 is the Environmental Protection Agency. They estimate that all landfills in the U.S. have leaching, and so we know that it has a possibility to exist, but we also have studied it, and we see examples of it, and we know that every landfill, according to the best scientists who work in the space, we have some leaching. after it's closed, so we've finished it and we've capped it and we've done that whole process, just because we've walked away doesn't mean we've isolated its ability to cause harm. So we know that it can cause harm to the waterways. It continues to need to be monitored. So as we're building up landfills and creating more and more waste over time, we're also committing ourselves to having to monitor those and make sure they're not causing harm 10, 15, 50, 100 years in the future. Decomposition does occur, especially with the material that's combustible. Decomposition, what I'm saying is microbes, microbacteria and microfungi are working in the space as they typically do. Biochemical cycles are working. And they're producing byproducts, most notably in the form of gases, get out into the environment. So carbon dioxide, because of cell respiration, methane as part of their digestive processes, and methane is extremely explosive and it's also a hazard. So these are the four things that we're really concerned about. Just the ability for these to cause harm to water, and then creating these explosive and climate gases that are associated with breakdown. Another way that we can deal with it, besides just putting it in a space and burying it underground, is incineration. This process is really popular because it reduces the amount of total solid matter that exists in front of us, converting it into most notably gas. So incineration, I'm going to do the same here and then we'll loop back through. So we take the waste and we dump it into a space like a bunker, and then we move it from the bunker using a crane or a hopper into this giant fire, and all elements that are combustible or can be burned in a fire are burned, and the waste is burned up in this chamber. We're using some filtration system, usually a baghouse filter, that helps clean the air. We'll loop back to this when we look at air pollution, but a baghouse filter is a key device that you need to have in your memory for AP purposes. But it helps clean the air before it goes out of the process, helps mitigate it. We have a whole bunch of material that cannot be consumed by the fire, and it creates ash. So the ash falls down to the bottom and we can collect it and remove it. And if we're lucky, we can use the heat energy to create electricity or to generate heat to heat a building or etc. So some of the key things we're just talking, incineration is just burning the waste. Already covered that. The ash is the residual inorganic material. So anything with carbon and oxygen is going to be combusted and turned into a gas, but any other minerals or any other types of material are going to gather at the bottom. The bottom ash is the stuff that we can collect after the fire is done. We're going to manner that is generated as part of this process. It's just not as much as it is with the landfill situation. And then we have fly ash, which is this residue that we're trying to catch with the baghouse filter. So we have ash that's around in the air. We don't want to release that into the environment. So this filtering process helps capture it. And then the key thing we really like as part of this process, that we can turn that waste into an energy source. So you could put it on your list of, hey, all the available ways to produce electricity. Here's another way, burning waste. Everybody feel good here? Incineration. Somebody's throwing up out there. It's a little awkward, wasn't it? Like, tippity-tap, the notes are being taken, and one person's throwing up. It's gross. We good? These terms are pulled from the text, so this isn't the only opportunity to see them. But I'm happy to give a little more time here. You guys heard about the guy who was lasering Tom Brady during the Super Bowl? He got arrested. It's not cool, but also I support that guy. All right, next. When we looked at our total amount of material, and let me just go back here for a second. Number 4 is a huge issue, right, that we just talked about. Microbes are decomposing and generating these harmful gases. This is one of the major environmental consequences. What they're breaking down is organic material. So here I'm going to zoom forward back to composting. When we did our calculations, we saw that about 1/3 of all of the solid waste, 1/3 of 2 tons generated per every household goes to a landfill, even though it's organic material that can be broken down through normal environmental processes. This is a huge thing. So we're causing an environmental consequence to happen associated with landfills that doesn't even need to exist. And it's a huge amount. It's not a significant amount. It's 1/3 of the total waste. So it's a lot of stuff. We have a process in place where we can leverage the ecological services that normally would happen with decomposition and turn this into really valuable material. This is what that process looks like. So you take the waste, it has to be just the compostable material. It can't be other stuff that won't break down or the whole system becomes unuseful. But if we take the waste, and all waste then, right, just the composting waste in number 1, and collect it in a certain space, we can separate it and put it into slightly different categories. Anything that's not compostable will be removed, but the parts that are organic material, like food or yard, other organic material like that, we put it in large piles or big furrows and then turn it over so that it can breathe and the microbes can work. And all we're doing is allowing natural biogeochemical cycles to take place. We turn this waste into super valuable soil. Some of the best soil that you can buy for like $1 for 40 pounds, which I know doesn't sound like much, but keep in mind you're taking it from waste. You eliminate an environmental consequence and you create something that's valuable economically and valuable ecologically just by letting this process take place. You just lay it out and turn it over every once in a while. What could be more simple than that? And you turn waste into black gold. Beautiful soil. So what we're talking about here is this creation of this organic matter, or humus. If you remember when we talked about soil, the organic material, which is one of the most valuable horizons on the top of the soil, is made of this same kind of stuff, humus, and it's created by biogeochemical cycling of small microbes. So this is a really huge opportunity in our society. One of the biggest companies in the United States who does this is just right down the street from our school on Page Avenue, St. Louis Composting. They do this, and they collect from businesses and places like our school, and they turn waste into valuable stuff. All right, a couple more key things here, and then we have an active exercise to answer some key questions. Hazardous waste. Hazardous waste is in its own category. So looping back to what I said before, not all waste is equal, and its eventual destination or fate is largely based on what kind of waste is it. If it's compost, we can quickly turn that into something good. If it's hazardous waste, we have to deal with that in a very specific way. The word hazard, I know you probably have a definition around this, but it has an ability to cause harm. The ability to cause harm is very high. So it's much more dangerous and potentially harmful than a regular pollutant. A couple examples: liquid, solid, or gaseous sludge waste that's created it can cause a lot of harm to either humans or the ecosystem. So things we're talking about is the waste from nuclear energy sites that has the ability to cause harm. It takes a very long time for it to break down. It has radioactive properties. That would be considered a hazardous waste. Something like ultra-concentrated bleaching solutions or things created by manufacturing processes, those can also be considered hazardous waste. It doesn't always have to be radioactive material, but they have a very likely potential of causing harm to either humans or the ecosystem. So they have to be dealt with in a certain way. These are two key terms that you need to know around hazardous waste that come up on a lot of AP environmental science standardized tests at the end of the year. A Superfund Act and a brownfield. Let's take them just one at a time. So a super fund is a fund that the government has set up through legislative processes that allow for the cleanup of hazardous waste if the company is no longer in business. So normally, if I'm a company, it would typically operate like this. I'll take care of my waste, and I'll pay the government, and I'll deal with it in this way. But businesses have a life cycle, or processes have a life cycle, and a lot of times companies go out of business. Well, in the future, in 50 years, say, we figure out that that waste is causing a great amount of harm in the environment and it needs to be mitigated. Who's going to take care of that? The company is gone. They can't be accountable anymore. You can't go to the company and sue them. They don't even exist. So we set up, because this is so important and it has the ability to cause a lot of harm to human health, we've set aside a certain amount of money that can be tapped into and used for these purposes to clean up in these cases. So a super fund, as the word would imply, it's also known as the CER-CLA Act. You don't have to know that. But the super fund, it's the funding piece, that's the part that really matters. And the super is, it's supplemented by the government. This map here shows where all of these are in the United States. So these are places where we have no accountable body except for the government. The super fund is the only thing standing in the way and paying for the research and the mitigation efforts between the hazardous waste and ability to cause harm. Quickly look at this graphic. Where do you see a clustering of hazardous waste sites?
New Jersey.
In New Jersey? Lots of people in New Jersey, or no?
No.
So part of this is because there are a lot of population centers in these areas, but there's also a lot of waste being created by industries in those same spaces. What do you notice about our region?
There's a lot in St. Louis, not much.
There's quite a few right here in St. Louis. There's a couple that are proposed. We have some of the most dangerous Superfund sites of anywhere in the United States within 25 miles of where we stand right now. So if you think this kind of issue doesn't affect you, think again. More on that in the future. Brownfields are contaminated industrial commercial sites. So a place where an activity or a process was taking place at one point in time, and now it's hazardous, and it may require cleanup before it could be used again. So say you have a tire factory, and it's not very environmentally friendly. That company goes out of business, and there's a concentration of pollutants there. It has to be cleaned up before other people can come into that site and use it to build homes or industry or things like that. So we have to have a lot of government intervention in this space. And that's not a political statement. It's a reality of there has to be some way of dealing with this. Every country has a different mechanism, but every country in the world that's a developed country has a process to deal with this because of the great potential to cause harm. Okay? Okay, last little thing here we want to talk about. The waste stream is being generated. It has the ability to cause harm. How can we move items away from the waste stream and cycle them back in and deal with them in different ways? So, electronic waste, heavy metals, electronic components, it has the disproportionate ability to cause harm in the environment, but it also has a huge economic value. There's platinum in computers and DVD players and TVDs. There's gold in microchips. There's all kinds of key metals that are used, and they're very hard to mine, and they make a lot of the technology that we use. Those wastes and the plastics and the wiring and all that, they have a disproportionate ability to cause harm in the environment beyond normal, like food trash as an example, but they also can be recycled and repurposed, and so we call that whole thing e-waste. And this infographic is really nice, but the piece that I really like here is this map right here. What you see is the places that create e-waste, like developed countries like the United States, move that material to other places in the world. So this version of, hey, we're creating waste in our house and then we move it away and we don't have to deal with it. E-waste is like that on a macro scale. We're creating waste by the movement and the development of our society, and there's waste associated with that, but we're removing it and moving it to other countries for it to be dealt with. This is a version of environmental injustice which is really key for us to deal with. It's about 2% of the waste, but if we recycle it, we can reclaim some of the most valuable elements and put it back into the input stream of our society. This piece I want to move through fairly quickly, so there's going to be some, it's kind of a text-full slide, but a lot of it is really intuitive, so I just want to brush up on your knowledge on some of the key concepts. So here is, again, the total amount of waste. About 54% is discarded, but a certain amount can be composted or reused or recycled, and then we can do some combustion and energy here. So we're going to focus on this green section here and talk about the 3 R's. The 3 R's are reduce, reuse, and recycle. You know this from 6th grade, 4th grade, kindergarten maybe. So source reduction is reducing the total amount that goes into consumed goods. What's really nice is as a part of source reduction, it also improves the efficiency of overall processes, especially in the manufacturing space, but it also minimizes the problem with transporting and dealing with waste on the back end. So if you reduce the total inputs, you reduce the total waste that's being generated. That's really nice. Source reduction also usually means substituting less harmful, using a harmful product and replacing it with something that's less harmful. We've done a really good job in the last 20 years of doing that in the United States. Reuse. So after a product is used, like a glass bottle, instead of recycling it, why not just reuse it for the same purpose? There are all kinds of, this is, well, let me just continue on here. Optimally, you don't have to use any additional energy, right? Because you're just totally repurposing and reusing that item as it is. And it also reduces the amount of energy required, so that's pretty nice. But you might still have to move it back to the manufacturing plant so that it can be refilled or whatever. When I was a kid, we refilled our glass bottles at the grocery store and with heat goods. We don't do that process very much in the United States anymore, but it's a huge opportunity. Recycling is the one that you know about so far. You've thought about a lot. You take a good and then you put it and you repackage it and turn those inputs in. We're going to focus on 2 key things, closed loop recycling and open loop recycling. I'm going to just jump to the next slide here because I have those definitions again. In a closed loop recycling methodology, you're taking the material and you're breaking it down and turning it back into the raw material and then turning it directly back into that finished good again. So no new stuff. No new product being made. You're just breaking it down and then using the raw material to turn it back into that final good again. They use this carpet as an example here. In an open loop, so you say you have something like they're using petroleum here and it creates a plastic bottle and then you recycle the bottle and it goes to a processing site and you reuse that plastic instead of making a plastic bottle again, it might be turned into something like a shirt. So the final destination of that material is different, even though it's made out of the same inputs. That's the difference between open and closed. I have this here as an example. We're going to skip this exercise because I'd rather do my exercise on the next slide, which has a little bit of media interpretation on it as well. But you can think of all kinds of things that exist in this space. So here we're going to do a little work with a free response question around this media news thing that we're going to listen to, thinking about sustainable solutions. So here's the questions, these 4 questions that I want you to answer, and we're going to listen to this short 2-minute radio clip that goes along with this.
This is the Marketplace Morning Report. I'm David Brancaccio. Recyclers along the West Coast are in crisis mode. That's because China is no longer willing to buy nearly as much of the recycled goods that they once did. They say the shipments are too jumbled up with non-recyclable materials. U.S. municipalities and recycling companies are trying to figure out what to do with their growing heaps. Marketplace's Jed Kim reports on one of the many things they'll have to sort out: us.
Within minutes of meeting Heather Repenning, she says she thinks I'll be a
wastehead.
That's apparently not an insult to Repenning. She sets waste and recycling policy for the city of Los Angeles, and she calls herself a wastehead.
It's someone who is completely immersed in discussions, operations, and policy around the waste sector. Welcome to the world of being a wastehead.
One thing that keeps wasteheads up at night is the lousy job of recycling that non-wasteheads are doing.
They're hopeful that things will be recycled, and so they put everything in there. That's not what we want them to do. We want them to know what is actually recyclable.
About a third of what well-meaning Californians put in the blue bin shouldn't be. It's a problem because removing all that stuff takes time and money. That can make recycling uneconomical. So municipalities are stepping up their public education. More social media campaigns, more informational inserts in water and power bills.
The best way to educate people would be to have them come and visit one of our MRFs.
By MRF, she means a materials recovery facility. I went to one. It's a massive warehouse where bulldozers mound up mansion-sized piles of waste. Flattened cardboard boxes flop off conveyor belts. A lot of this stuff ends up in towering bales, ready to be sold. But a lot more of it is going to landfills because it's too contaminated.
It's probably 15 to 20% more than we would have otherwise.
Bob Asgian is with LA County Sanitation District. He takes me up to where dozens of workers snatch out contaminants from a high-speed sorting line.
I see a diaper,
Idiocy. But then we see...
envelopes with plastic laminated on them,
Wait, I've tried recycling those.
plastic casing for fruit,
Oh, done that too.
a beer bottle case.
Oh my god. Hold on, beer boxes are contaminants?
Next week, who knows? But this week it is.
That's because recyclers can't just pass chipboard beer boxes and other mixed paper along to China anymore. What was once in demand is now a glut. Mark Oldfield is with California's recycling agency.
If there's no viable market for it, is that something we want to continue to call recyclable?
And that underlines the need for more public education, because we could all be better waste heads. I'm Jed Gibb for Marketplace.
All right. I'm going to put these questions on canvas because we're short on time, I know, and with the radio clip. What we should do, hold on, don't get too excited. We have to start improving our abilities and getting ready for the AP test. This is the exact type of thing that you would see. You would get 10 minutes to answer a question like this. So I'm going to put it out there, and it's a good opportunity on something that's fresh in your mind to practice this kind of exercise in pre-response question writing. I'll put it out there, and then we'll start our time next time we see each other, just discussing how it would be answered and how points would be allocated. So you'll see that. I'll see this group tomorrow. Have a fantastic rest of the day.